Welcome to Brain Vision.
Hi everyone, so what we have is a feed water system that is getting heated up by steam. So we have steam going from 1 to 2, and we have feed water going across from 3 to 4. So we know that the incoming pressure of the steam is 1 megapascal and the temperature is 200 degrees C. And that steam exits at, again, 1 PA as saturated liquid. The feed water enters the circuit at 2.5 megapascals and 50 degrees C, and it leaves at the same pressure but at a temperature that is 10 degrees less than the pressure of the steam at its exit. What we're asked to find is the ratio of the m dot of the steam over the m dot of the feed water. So what we're going to do first is state our assumptions. We know that the system is steady state, so nothing is going to be changing with time. We're also going to be assuming that any changes in kinetic and potential energies are negligible. We're also going to assume that there are no work interactions. And we're going to assume that any heat loss from the device to the surroundings is going to be 0. Therefore, that the heat loss coming from the hot fluid is equal to the heat loss coming in to the cold fluid. Next, what we're going to do is we're going to define our properties and look these properties up through the table. So for the steam, what we're going to do is we know that the incoming pressure is 1 MPa and the incoming temperature is 200 degrees C. Knowing these two quantities, we can figure out that we can look up our incoming enthalpy to be 2,828.3 kilojoules per kilogram. And we can also use the exit parameters of the steam. We know the pressure is the same at 1 MPa, and we also know that it exits as a saturated liquid. Therefore, we can look up the exit enthalpy, and that's going to be H2, which is going to be equal to HF at 1 MPa, which is equal to 762.5 kilojoules per kilogram. And this occurs at a saturation temperature of T2 equal to 179.9 degrees Celsius. We can also do this for the feed water as well. We know the inlet state of the feed water. We know that the pressure, P3, is 2.5 MPa. And we also know the temperature is equal to 50 degrees C. And therefore we can figure out and look up our enthalpy, which will be H3, and this will be the HF at 30 degrees C, which is equal to 209.34 kilojoules per kilogram. We can also look this up. We can also do this for the exit state of the feed water, because we know that the feed water is at the same pressure of 2.5 MPa. Now recall that we are given that the exit temperature of the feed water is 10 degrees less than the exit temperature at the steam. So we did solve and look up the exit temperature for the steam to be 180 degrees Celsius. Therefore, we can say that our exit temperature of the feed water is 180 minus 10, which is 170 degrees Celsius. And by using these two quantities, we can look up the exit enthalpy, and that's going to be H4, which is going to be HF at 170 degrees C, which is equal to 718.6 kilojoules per kilogram. So now what we can do is define our system. We're going to define this heat exchange as our system, and that's also going to be the control volume. So now what we're going to do is do a mass balance for each fluid stream. So just in general, we know that the mass coming in minus the mass leaving is equal to the change in mass of the system. We did assume that this system is steady state, so this change in mass of the system is going to be 0. Therefore, we know that m dot in is equal to m dot out. Now, if we use the same state nomenclature as we did for the pressures and temperatures, we can say that m dot 1 is equal to m dot 2, and we're just going to call that m dot steam. We can also say that m dot 3 is equal to m dot 4, and we can call that m dot floodwater, or feed water, excuse me. Now we can do energy balance for the heat exchanger. In general, the energy coming in minus the energy coming out is equal to the change in energy of the system. Now we are assuming this is a steady state, so the change in energy of the system will be equal to 0. Therefore, E dot in is equal to E dot out. Now we can break this E dot and E out into its constituents. So for E dot in, we can say that we have both the feed water and the steam coming in. So that's going to give us M dot S H1 plus M dot FW H3 is equal to M dot S H2 plus M dot FW H4, because we are assuming that work and heat transfer are negligible. Now what we can do is we can combine this equation with, we can actually go ahead and just combine like terms actually. So after combining like terms, what we get is M dot S H2 minus H1 is equal to M dot F H3 minus H4. We can just divide both sides by M dot FW and also bring this H2 minus H1 over to this side. And what we have is M dot S over M dot FW is equal to H3 minus H4 all over H2 minus H1. And we actually have all of these enthalpy values that we looked up in the table. So by plugging in these enthalpy values, what we get is this ratio is equal to 0.246, and that is the ratio of our mass flow rate of steam over mass flow rate of the feed water. And this is our final answer.